You're much better than last year's class. Last year I had to like yell for 5 minutes until people would stop talking. Thank you. All right. So I've spent some quality time with this tablet, and I hope it's not going to misbehave again today. But now that I've said that, things are going to go wrong. But let's see how we do. It's a learning experience. IS 106, Lecture 4. We've got 80 minutes together today. Today is a big 80 minutes. We're going to learn a lot today. We're going to go into 3 dimensions and then back into 2 dimensions. We're going to solve equations. We're going to do a proof. I mean, it's going to be crazy today. So if you saved your granola bar for after class, maybe have it now. All right. So fasten your seatbelt and let's go. So last time where we were. Is we basically finished up preferences, all right? We all agreed that you have tastes over all kinds of things, and I said that the only thing I need for your tastes to be, I need them to be complete, meaning you can rank bundles, or you can tell me that you're indifferent between them. You're not allowed to say, I don't know, right? I prefer A to B or B to A, or I'm indifferent between the two. They have to be transitive, that if you prefer A to B and B to C, you definitely prefer A to C, right? They have to be consistent. And non-satiable is just a fancy word for more is better. You always prefer more of something to less of something. Also, keep in the back of your mind, for those of you who are already envisioning, what it's like to purchase things in a supermarket, you're actually going to have to pay things at the end, right? There's prices, and your purchase decisions involve prices. We're not there yet, right? We will get there, but right now, all we care about is your preferences over things as if they were free, right? That's where we are. What these 3 properties on preferences get me is you may never ever draw an indifference curve that crosses another indifference curve ever, even after this class. They're always nice and thin, which means carry a pencil sharpener or buy yourself one of those nice Japanese drawing pens that are super thin, so nice thin indifference curves. They cannot be upward sloping, all right? So they're always weakly downward sloping. There's one that's flat in certain parts. Anybody remember which type of indifference curve is actually not downward sloping, but it's flat in some parts? Perfect compliments, right? It's flat at the bottom, so it's weakly downward sloping. All that means is, it can be flat or it has to be downward sloping. It cannot be upward sloping, all right? So we talked about 3 types of indifference curves. We talked about imperfect substitutes, which are these. Come on, Max. So excited about this, and I had my carb-loaded granola bar, so I'm talking 1,000 miles a minute. Imperfect substitutes are these nice sort of bowed out or bowed in, depending on which side you're standing, indifference curves, right? They're the ones we drew in the beginning. The first one we met. They're these ones. Those are the ones you'll encounter most of the time, and they imply that you're willing to substitute between the 2 goods you're drawing at a varying rate. The rate at which you're willing to substitute between Reese's and Hershey's is called the marginal rate of substitution. How many Reese's are you willing to give up in order to gain 1 more Hershey's while maintaining your level of happiness? Perfect substitutes are straight line indifference curves where you're willing to substitute between 2 goods at a constant rate. If they're same size water bottles, that marginal rate of substitution could be 1. You're willing to exchange 1 for 1, but it could easily be a 4-to-1 rate, right? I'm willing to exchange 2 16-ounce Arrowhead bottles for 1 32-ounce Dasani bottle at that rate forever because they're perfect substitutes to me. So constant marginal rate of substitution. The last type of indifference curves we have are so-called perfect complements, where you like things in fixed proportions. Unless you have Velcro shoes, it's nice to have 2 shoelaces with each pair of shoes, right? One's too little, and the third one, it always ends up in a drawer, and when you're looking for your screwdriver, there's that shoelace there, and it's just annoying. It doesn't help anybody, right? And then stuff gets tangled. So there are lots of goods that we like in fixed proportions. We will, down the road, encounter one more type of preference. Those are called quasi-linear preferences, and since they sound so terrifying, I didn't want to pack too much into the beginning of this class. We'll deal with those later. Guess what? They're quasi-linear. That's why they're called quasi-linear. All right. So what we said last time is I am going to construct something called a utility function, where I'm going to assign numerical values to levels of happiness, right? These units are called utils. They give me an internal ranking of what my level of happiness is. But if I'm currently experiencing 1,000 utils and you're currently experiencing 200 utils, it doesn't mean I'm happier than you are. That just means at my current level of consumption, I have 1,000 utils. If somebody now offered me a nice piece of gum, my utility would go up to maybe 1,002. It just means that new bundle, current consumption plus 1 piece of gum, is preferred to the old one without the piece of gum. So utility just allows you to internally rank bundles. What I then did was this ridiculous performance piece where I said Hershey's increase along this wall and Reese's increase along this wall, and everybody all day kept on commenting, Max, you have chalk all over your coat. And I said, yes, I teach micro. Come on. Totally all right. So the point here was utility starts at 0, and then this defines the plane of Hershey's versus Reese's, and anywhere I stand, like on a chessboard, gives me a location of a given bundle of Hershey's and Reese's, a combination. Then I can figure out what the assigned level of utility is that I know, that you don't know, but I can feel it with my soul. I assign a numerical value to it, and I walk around and I think about what that level of utility looks like, and in some sense construct this 3D surface of utility over the space of Reese's and Hershey's. Now, I usually get the first set of comments on these chat sites when I had the chat feature enabled. Max has lost his mind. That may be true, but let me show you what this looks like in 3D. Because sometimes visualizing these things is a really useful thing to do. Let's use a real computer. Okay. Come on, Mac, don't let me down. There we go. Okay, this is MATLAB, one of my favorite programs in the entire world. And what I'm going to do is I wrote a little bit of very simple code, and I'm going to run it. And out come some graphs. Away, you graph. I want to look at you. Beautiful picture. Wow, isn't that gorgeous? Meet your first utility function. It's in 3D, right? So what do we have here? For you in the back row, I'm sorry, I used a very small font because I don't know how to increase font size in MATLAB. But the point here is this is the origin, 0 Hershey's, 0 Reese's. Along this axis, I'm increasing Hershey's. Along this axis right here, I'm increasing Reese's. And I have actually plotted out my utility function. So this is a 3D surface where in the third dimension now is my level of utility. So this thing looks pretty cool. Now, get ready for why math is cool. Are you ready for this? The engineers in the room have seen this before. Yeah, see, that's what I was hoping for, right? So, Max was standing here in the corner of the room, and then along this side here, so along this side here, that's this wall right here. This axis right here is this wall, and I'm just mapping out the utility function, so it's a surface, right? What do you see on the floor of that utility function here? You're already ahead of me, right? They're indifference curves. They're things that look like indifference curves. They're these nice sort of roundish indifference curves right here. So what these things are is I'm going to take a mathematical knife, and I am going to look at it from the exact side here. So let me look at it from the side. Okay, so you're looking right at the origin now. And to the left is increasing, the 45-degree line, or Reese's are increasing to the right on a 45-degree line. Hershey's are increasing. What I'm going to take is, at a level of 5 utils, I'm going to take my mathematical knife, and I'm going to cut through the surface, right, and see what the top edge of that surface looks like. And if I do that, the top of that surface looks as follows, right? So now I'm looking from the top down, Hershey's here, Reese's here, and here are the sort of edges of slicing that surface at a level of 5 utils, 10 utils, 15 utils, 20 utils. So each of these lines here tells me the combinations of Hershey's and Reese's that I'm indifferent between at a low level of utility, at a slightly higher level of utility, at an even higher level of utility, at the highest level of utility. So what this is, it's a topographical map of a utility function, right? It's the same thing I showed you last time with Mount Everest, where I showed you this 3D picture, and then we looked down and just showed the topographical lines. So this is what a utility function and the corresponding indifference curves look like for imperfect substitutes. Now, Max, you think you're so cool. Not really, but I know my limitations. What does a utility function look like for perfect complements? Welcome to Giza, right? No, I'm joking. It looks like a pyramid, right? So it looks exactly like a pyramid, so I can rotate this around for you a little bit if you want. It doesn't look exactly like a pyramid, but kind of. Right, so we can rotate this around, so you see how this is like bent, and then if you look at the bottom here, if I slice that pyramid-shaped thing at any level of utility, 5, 10, or whatever, I get level sets, is what a mathematician would call it, or what we call it here, indifference curves at different level of utility, and because these are perfect complements, these things look L-shaped, right? So if you look from the top down, which I could do with this particular thing here, but then you just see the top of the surface, so I've made a second graph that just plots the slides, so you get these L-shaped indifference curves. So utility function for perfect complements looks a little bit like a pyramid. For imperfect substitutes, it looks like a basketball cut into 8 pieces, 1, 2, 3, whatever, a bunch of pieces, like a, you know what I mean. And for perfect substitutes, it's just a plane, right? A plane that you cut at different levels. So hopefully that made that concept of how we go from utility function to indifference curves a little bit more, I don't know, easy to understand. None of this stuff is easy to understand. All right, come on, wire. So that's that. Last time then, I gave you a homework. And 3 people came to my office hours, which was an all-time record for first office hours held. Average attendance in my office hours when there's not a midterm within 2 weeks is usually 0.2. Nobody comes to office hours. I don't understand that, right? You get free consulting from the guy who writes the exams and you don't show up. Makes no sense to me, but you figure it out. So come to office hours. So what I asked last time is, are bundles further away from the origin always preferred? And the answer is no, right? But I wanted you to convince yourself that that's the case. So let's pick one bundle here. Let me just make sure. This one and this one, okay? Bundle A, bundle B. If we measure the distance from B to the origin, it's really far away, right? If I measure the distance to A, it's not that far away. So A is closer than B. So somebody who didn't take 106 and didn't pay attention last time would simply say, well, B is further away from the origin, so I must like it more because it seems like it has more stuff in it. It doesn't. It's just a different combination of things, right? B has more if on the x-axis we have Hershey's and fewer Reese's, and A has more Reese's and fewer Hershey's. So you don't have more of both things in one of these bundles, right? One has relatively more Reese's and the other one has relatively more Hershey's. So let me show you a scenario here where A is actually preferred to B. This takes years of training. A. Those are some ugly indifference curves, right? But the point here is B has this indifference curve that goes through it, and A has this indifference curve that goes through it. So for this particular individual here, A lies on an indifference curve that's further away from the origin along a straight ray than this indifference curve. So draw a straight ray. You could draw it through A if you wanted to, but you don't have to. I'm going to do it. Right? So draw a ray from the origin. Indifference curves that are further away from the origin along the same ray are preferred, right? So I prefer this indifference curve to that indifference curve. So since A is on this indifference curve and B is on this indifference curve, I prefer A to B. Does that make sense? So this is one of these check your understanding, Bill Nye the Science Guy type things. Try and draw this, try and talk you and your friends through this to make sure you get this part. What you like more than which bundle you prefer is determined by which indifference curve is on and how that indifference curve relates to the other ones that you've drawn here. And the ordering depends on where along that straight line from the origin you are. Okay, so check. Here we are. This is where it gets tricky. So I was told when I was hired here many moons ago, Max, thou shalt teach economics to a classroom full of students who do not want to learn economics but are required to, and thou shalt not use calculus ever. So I said, okay, I really want to work at Berkeley. I'll figure it out. So I love it here. Still do. Greatest university in the world. But I think I figured out a way how to do this without calculus by basically cheating you into thinking you're not doing calculus when you're really doing calculus. Okay. So what I'll always do when calculus concepts come in handy, I will explain it without calculus, and then I'll give you the short version of what this means in calculus talk, so both sides of the room can understand what I'm talking about here. So this concept that we're going to talk about here is called marginal utility. So where economists are different from most other social sciences and engineers is we spend a lot of time thinking about where you go from where you are, right? What does a one-unit change do to you or a firm's behavior or a group's behavior relative to their starting point, right? We're not really that interested in average behavior. We're interested in what people are doing once I give them a tiny little nudge and where they go from there. And by nudge, I mean a change in the price signal or more information or anything like that. So one concept that's really important here is this concept of marginal utility. Marginal utility in words just simply means the additional utility you get from consuming one more unit, right? So the marginal utility of Reese's is simply how much does your utility, that number of utils, change by as I give you one more Reese's. And here comes the kicker. I'll say it in Latin first. Ceteris paribus. I can say it in German Latin too. Ceteris paribus. However you want to pronounce it. Yes, I took 9 years of Latin and I've forgotten everything except for that sentence. But holding the rest of the world constant, right? Everything else equal. So what you're doing is you're freezing the world, like in a physics experiment. You're holding everything constant, right? Nothing else changes, but you're giving that person one more Reese's, right? So freeze the world, give that person one more Reese's and see what happens to their utility. So how much does your happiness change? I'm not really that interested in how happy you are in these models often because that doesn't really determine behavior. But what does determine behavior is these things here called marginal utilities of different goods that tell me how much your happiness changes by consuming one more unit of different goods holding everything else equal, right? So let's think about this for a second. How much would your marginal utility go up by if I gave you that new Tesla with the 2 engines in it? Anybody seen that thing? Right? There's now a Tesla that has like 400 horsepower in the back and 300 in the front. There's a video online where this guy puts a bunch of people in it and floors it, and people use swear words I've never heard before in my life. It's an amazing car. It'll make your Bentley look like a child's toy, right? How much would your utility, sir, go up by if I just handed you one of those Teslas? A lot, right? So 100,000 utils is a lot. How about if I offered you a number 2 pencil? Okay, see? So the thing here that we've already, thank you for answering truthfully. So the thing we're already noticing here, the marginal utility from different things, right? Getting additional amounts of different things give us different amounts of additional utility, right? Often things that are extremely valuable give us lots of additional marginal utility. A Tesla is a really nice thing, costs, I don't know, 150 grand or something like that one, if you want the math. Number two pencil, they're essentially free, right? If you just walk around campus, you can pick them up. So one thing we're noticing, we're going to have to do something about price here, but if we step back for a second to a more basic concept here, is it also depends on how much of something we've got already, right? The starting point matters. So I in my office have about 300 number two pencils, because I like those pencils a lot. I get a German brand because they're blue, not yellow, all right? And I do all my math with these. So if you gave me one additional number two pencil in my office, my marginal utility from one number two pencil, even if it's a German, is just not very high. Versus if I'm stuck on an airplane and I forgot my pen and I really want to do some math, and the person sitting next to me notices my desperation and hands me a blue German number two pencil. How high do you think my marginal utility is? I'm going to hug the guy. I mean, I'm going to be so excited, right? So the additional amount of happiness you get even from the same good really depends on often how much of that good you already have, right? So marginal utility is not something that's individual specific for a certain good, but it depends on the individual and how much of that particular good you already have, the size of your stash, right? So marginal utility, the important thing here is where you start matters, meaning how much you have, and the other thing to remember here is that marginal utility holds everything else constant. There's no change in information, there's no change in the amount of other goods that you have to give up, so there's no trade-off involved here in the concept of marginal utility. You just get one more unit of Hershey's, how much does your utility go up, holding everything else constant? That's the thought experiment. Okay, graphically. Damn it. I changed this. Oh no, this is right. Sorry. Let me just see one thing. That comes later. No, this is right. Okay. I changed the slides a little bit, so if you printed them out last night, I'm sorry, right before lecture I made a couple of numerical changes. I will point out where those are. Okay, so this one's the same as what I put online. So let's figure out what marginal utility is. So if you have 0 Reese's, you have 0 utility. So if I give you that first Reese's, right, at 11:33 at the end of January, right when that, wow, it's 13 more weeks till this class ends moment sets in, and I give you a Reese's, your utility, your marginal utility, I argue here is 25. Let's say this is my marginal utility. So I go from 0 to 25. My change in utility from one additional Reese's is exactly 25. Now you offer me a second one. My overall utility is already 25 because I've had one, but my utility rises because I like more Reese's more better, right? So I go from 25 to 40, so my marginal utility is the change in utility from one more Reese's, so it's 40 minus 25, it's 15. Give me one more Reese's, a little bit of a piggy, right? I'll go from 40 to 50, my utility goes up by 10, 50 to 56, 6, 56 to 64, 60 to 62, 2. Right? So what we're already noticing here is that my marginal utility starts really high and slowly starts diminishing. Right? For those of you who choose to drink beer, drink sparkling water instead, better for you. But, the first beer often tastes really delicious versus the 17th beer not so much. Right? Same thing goes for most of these goods. Again, presenting information in table format is not the preferred format to present anything, so we can draw this. Right? What I'm going to draw on the top panel here on the right is I'm going to just draw overall utility against the number of Reese's, and in the bottom part, I'm going to draw the marginal utility against Reese's. So basically take this second column in this table, draw that in the top one, and the third column, draw that in the bottom of the graph. Okay? X-axis here is Reese's. Y-axis is utility. So we start 0, 0, 1, 25, 2, 40, 3, 50, 4, 56, 5, 60, 6, 62. So I can connect this thing, and it looks something like this. Right? That's my overall utility of having more Reese's, holding everything else constant, right? Holding the amount of Hershey's constant. Now I'm going to plot my marginal utility against Reese's. Marginal utility starts at 1, 25, 2, 15, 3, 10, 4, 6, 5, 4, 6, 2. We can connect these dots. So this is my utility function, and this is my marginal utility of Reese's. So utility, as I give you more Reese's, goes up, right? You always become happier as I give you more. That's the more is better assumption. But the additional or incremental amount of additional happiness you get from consuming one more, holding the amount of Hershey's constant, drops, right? This is the beers in a bar thing. First one good, second one still good, but less good, and so on. If we're thinking about beer for a moment, your marginal utility may actually become negative, right? After the 17th beer, you'll probably get sick, and you're worse off than would you not have had that beer. Generally speaking, that violates the more is better assumption, right? Clearly. But the notion here is there's a time lag between consumption and when you realize what the consequences actually are. So these dynamic problems don't fit in here very well. We could work with those, right? But I'm going to rule out things where you intentionally do things that give you negative marginal utility for now. I assume you're all Berkeley students and you don't do such things, all right? So that's utility, that's marginal utility. What I'd like to propose is a law of diminishing marginal utility, right? Utility goes up, happiness goes up as you consume more, but incrementally, the additional happiness you get becomes less. So this is I already sort of said this, but I'm going to say it again. Here I use chocolate bar because you may share these slides with your parents. Plus, I keep on getting these emails. I get emails. There's this one guy in Pakistan who watches this lecture. It's really cool. So he said, I enjoyed your lecture last week. I didn't understand graph 2. Can you please explain? Because they watch it on iTunes U. So hello, world. I'm glad you're listening. It's probably just one guy, but, who knows. But the notion here, and this is really important to not just memorize, but to really intuit that, right? As your consumption of a good goes up, as the size of your stack or stash of that good grows, you get less additional utility from one more unit of that good. It's not just beer, it's not just chocolate. Even after a soccer game, 90 minutes of full-on running, right? That first 16-ounce cup of water, amazing. But after the gallon, right, you're sort of done. You get very little additional utility from more water. So